Good morning, everyone. This is Dr. Venkateswarlu, working as a professor of UCE at IARE, Hyderabad. Today we'll be discussing about symmetric and antisymmetric finite impulse response filters. Before entering that, these are the contents. Design of linear phase finite impulse response filter with the windowing techniques and frequency sampling methods and equiripple linear phase finite impulse response filters, Parkes M-sequence algorithm and Ramage algorithm, least mean square error filter design, design of finite impulse response differentiator, MATLAB programs of finite impulse response filters, comparing with the recursive, either it is recursive or non-recursive. So finally, by using this all content, we will try to verify that that is symmetric and antisymmetric FIR finite impulse response filter. After that, comparison of finite recursive, non-recursive filters like IARE and FIR digital filters. Now coming to this introduction on this non-recursive filter finite impulse response. So far, our treatment of digital signal processing has focused primarily on the analysis of discrete system. So now we finally have the analytical tools to begin to design discrete time system. The discrete time system, it is coming from the DCT or CTC and so on. So for this case, the analytical tools to begin to design discrete time systems. So all LTA linear time invariant systems can be thought of as filters. So at least for linear time invariant systems, to design a system means to design a digital filter. The digital filter may be this IARE and FIR filter because of that importance of a digital filter when compared to IDEA and what you call analog filter. Okay, so the design of nonlinear or time varying systems is generally more complicated because of using nonlinear time varying systems. So based on this design, based on the components and other procedure and so on, the design of nonlinear or time varying systems is generally more complicated and often more case specific. So our goal is given the desired is magnitude response and phase response, tolerance specification and so on. Under introduction, so rational that is followed by H of Z. So linear time invariant system described by a constant coefficient difference equation that is followed by, so can be implemented with the finite of adds, some multiplies and delays. In other words, filter design means choosing the number and locations of the zeros and poles, or we can consider equivalently the number and values of the filter coefficients, and thus H of Z, H of N, H of omega. So this is the overview for identifying, for analyzing the order of the filter based on the order of the filter or a tap or whatever it is. So where n is equal to 0, finite impulse response or all 0. So if it is that linear pass band phase. If it is capital N, order of the filter is greater than 0, the infinite impulse response, that is non-recursive filter, digital filter, easily can identify based on that. So lower side lobes for same number of coefficients. If it is n is equal to 0, what do you call non-recursive filter. If n greater than 0, recursive filter, that is IARE. So general consideration, ideally would like to that n and m, that order of the filter or tap, or we can consider that n plus m to be as small as possible for minimal computation storage. So causal for now, so poles inside unit circle for the stability, the causality. So we will focus on designing the causal distal filters since those can be implemented in real time. So non-causal filter design, best example for offline applications. So in is much easier, and many of the what you call same principle apply anywhere. So like this, then LTA linear time invariant system is causal if what you call input and output relationship, that output response is y of n depends only on the current and past input signal values. So impulse response is where h of n is equal to 0 for n less than 0. So system function number of finite zeros less than or equal to number of finite poles. Based on that, input output relation will be appeared. So find frequency response. What can we say that h of omega, that frequency response will be observed. So real fact is if h of n, the h of n impulse response is causal or casual, then so Pellery-Wiener theorem, it is based on h of omega, cannot be exactly 0 over any band of the frequencies, except in the travel case where impulse response followed by h of n is equal to 0. So furthermore, h of omega mod h of omega cannot be flat or constant over any finite band. So hr of omega and h of omega are Hilbert transform pair. This is the real facts for analyzing finite impulse response or non-recursive filter. Based on these all real facts, we will design according to real-time applications with the help of finite impulse response non-recursive filter. So therefore, they are not independent. So hence, magnitude and phase response are interdependent. This is the main fact, what you call the real factor. So thus, those ideal filters with the finite band of 0 response cannot be what you call implemented with a causal filter. If it is possible with the finite infinite bands of 0 response, so that is way. But this case, those ideal filters with the finite bands of 0 response cannot be what you call implemented with a causal filter. So instead, that we must design filters that approximate the desired frequency response. So it is followed by SD. So it is desired. So what do you call that? Desired frequency response. It is followed by what you call SD of omega. Okay. Yeah. Now coming to the characteristics of practical frequency selective filters. So no perfectly flat region. In fact, since causal filters cannot have a band of frequency with the 0 response, nor can they have any band of frequencies over which the frequency response is a constant. This is a characteristics of practical frequency selective filters. It is depending upon factors. No perfectly flat region. In fact, it is followed by in terms of particular band of frequency over which the frequency response is a constant. Proof of by contradictory, suppose h of omega is equal to c for omega 1 less than or equal to omega less than or equal to omega 2 with the corresponding impulse response h of n. So now define the new filter, that is g of n is equal to h of n minus c into delta of n. Like this, we can change that all h of n, what do you call that h of n, g of n and h of n or delta of n. Based on this, g of n, the new filter or desired or what do you call known or unknown filter. Within this, then the certainly g of n is also a causal, but g of omega is equal to h of omega minus c is equal to 0 for omega 1 less than or equal to omega less than or equal to omega 2, which is impossible if g of n is causal. Okay, yeah, if it is possible that g of n is non-causal. Like this certainly g of n is also a causal, but g of omega is equal to h of omega minus c. If it is h of omega minus c is equal to 0 for omega less than or equal to omega less than or equal to omega 2. Okay, so after that you can decide the factor that g of n is causal. So in the casual filter cannot have the band of frequencies with the zero response. Here they have the infinitely sharp transition between the pass band and stop band. So nor can they have a perfectly flat pass band. So typical realistic magnitude response looks like the following the parameters, following the notations. So practical things, it is practical filter design means choosing the delta 1, delta 2, omega c and omega s, and then the designing the order of the filter or taper, capital N, capital M, the coefficients. This is the N is the order of the filter, M is the taps, number of taps, where AK and BK are the coefficients, AK, BK to satisfy those requirements. Okay, so often one must iterate if it is N is decided, or M is also on how many number of taps. After that, how it is calculating, measuring, and verifying that coefficients like AK and BK. Okay, that AK and BK value to satisfy those requirements. So often we plot that magnitude of h of omega using decibel, that is 20 log base 10. What you call h of omega mod h of omega. Okay, so using this 20 log base 10 log base 10 h of that mod what do you call h of omega, the magnitude of h of omega. So express the ripple in the decibels as well as what do you call, note that the stop band ripple is not defined if it is a peak to peak. Okay, since the highest magnitude response in the what you call stop band is more important than the what you call how quickly the response in the stop band. Using this all where the dB is, that is 20 log base 10 h of omega, and express ripple in decibel as well as it is what you call the highest magnitude response in the stop band is more what you call important than the how the response in the stop band. This is the practical filter variation design by choosing the delta 1 and delta 2 or omega c or omega s and so on. So then design directly right to design using that order of the filter or taper, or maybe after that we will expect that number of coefficients based on the AK and PK. So we will satisfy that those particular requirements. So like this, in excess omega versus the magnitude h of omega, you were 1 plus delta 1. So in between 1 minus delta 1, between this unity 1, like this. So this is the passband ripple. Okay, this is all passband ripple will be up here. After that, now it is transition. Transit band is also observed. That's where in terms of delta 2, passband or stop band ripple and stop band portion, omega p and omega s. So like this, we have to verify that the stop band, how many stop band ripples are available, how it is ripples are varied, pass band to the stop band to the pass band, and what the transition band and stop band will be appear. Okay, so for example, application where normally why we are following this all or this scenario or considerations by using this application. Best example of application. Like in a CD, compare this digital crossover, separate woofer and tweeter signal distally inside the CD player. It is the separate woofer. A woofer or bass speaker is a technical term for a loudspeaker driver designed to produce low frequency sound. That is our desirability. Low frequency sound, typically from 5 Hz up to the 1000 Hz. The name and can consider a tweeter or a trebler speaker is a special type of loudspeaker that is designed to produce high audio frequencies. What do you call it? In entertainment purpose, people are using either DJ or whatever it is. They will export the low frequency sound. Sometimes they will export the high audio frequencies. So typically deliver high frequency up to the 100 kilohertz. So Twitter signal, Twitter or treble speaker is a special type of loudspeaker that is designed to produce. Okay, tweet boosters are intended to convert an electrical signal into a mechanical signal, electrical signal into mechanical air, distally inside a CD player, compact disc player, rather in analog at a speaker. These are all real time application purpose. They are following this all scenario. We tell somewhat it is interlinked or a digital filter. How it is interlinked, this all are. So why is the passband ripple tolerable in this context? Like it is, maybe we'll export a distortion. So some noise or unwanted particle will be appeared. How? So room acoustic acts as the another filter using that present our environment. So the speaker response is not perfectly flat. Okay, so it is based on that all environment. Keep filter ripple below these other effects due to that all environment. So we can consider for this all we know that it is produce the low frequencies within music known as the bass and some bass. Okay, amplified through the woofer, while a regular speaker can allow you to hear the bass. So your subwoofer enables the listener to feel what you call the sound. Okay, like this. Right, to verify that Twitter like this. Yeah. Imagine that now. Imagine that we have specified delta 1, delta 2, and omega c and omega s, and we wish to design the order of the filter, the tapper, and what do you call? Here it is order of the filter and tapper, and okay, what do you call the coefficients? A suffix k. Here it is A suffix k. Here this B suffix k. These are the coefficients. Okay, the coefficients should satisfy those requirements as mentioned above. Here we have two broad choices like finite impulse response and infinite impulse response. Where in infinite impulse response is recursive filter or finite impulse response is non-recursive filter. Okay, so we focus first on this FIR, finite impulse response. After that we'll focus on infinite impulse response. So this is the digital versus analog filter. So here in digital filter, high accuracy. In analog filter, here it is why you are using this all digital filter, like this all digital filter may be what you call FIR, finite impulse response. This is non-recursive, infinite impulse response digital filter. This is a recursive filter. This is the best example of digital filter. Why we are using the FIR and IARE filter? For the purpose of high accuracy. Okay, coming to the analog filter, less accuracy. and component tolerance here. This case, linear phase, yeah, we will expect that all while we are using the digital filter, linear phase finite impulse response filter. Okay, coming to the analog filter, there is a non-linear phase. We know that all importance with linear and non-linear phases. No drift to component variation in the digital filter. Coming to the analog filter, drift due to the component variation. Yeah, in digital filter, there is a flexible adaptive filtering possible. Come to the analog filter, adaptive filter difficult. And easy to simulate and design while using the digital filter. And coming to the analog filter, difficult to simulate and design. This is the drawback in what you call in analog filter. This is the major what you call a flexible while using the digital filter. Computation must to be completed the sampling period, limit to real-time operations in a digital filter. Coming to the analog filter required at high frequencies and for anti-aliasing filters. Yeah, coming to the digital filter requires high performance analog to digital converter, digital analog converter, and digital signal processors processing. Coming to the analog filter, no, there is no analog to digital converter, digital analog converter, or DSP required. This is the distinguish between digital and analog filters. So, due to these all types of digital filter, we know that all moving average finite impulse response FIR. In FIR, suppose you have to verify that we will verify the linear phase. Easy to design due to this all are computational intensive. Thus, we always they prefer that all particular finite impulse response. Coming to the infinite impulse response, based on classical analog filters, computationally efficient, and lattice filter can be we can use either a finite impulse response and a infinite impulse response filter. After that, we will verify that under digital filter adaptive filters. Yeah, then the types of filters, due to this, there are two fundamental types of the digital filter. This now we have verified. Finite impulse response, FIR, and infinite impulse response, IARE. So, as the terminology suggests, this classification refers to the filters impulse response. Filters impulse response. By varying the weight of the coefficients and the number of filter taps, which is followed by capital M. In IARE they are in the capital N, but in FIR they will use that all capital M. Okay, so virtually virtually any frequency response characteristics can be realized with an finite impulse response filter, FIR digital filter. Other as been shown, like in a finite impulse response filter can achieve performance levels which are not possible with analog filter. This is the main merit, main advantages techniques such as the perfect linear phase response, where we are using the FIR finite impulse response filters. However, high performance finite impulse response filter generally require a large number of multiply accumulates and therefore require fast and efficient DSPs, digital signal processors. So, on the other hand, IARE, infinite impulse response filter, tend to mimic the performance of the traditional analog filter and make use of feedback. This is the major what you call concept based on this digital filter, like finite impulse response and infinite impulse response, maybe recursive or non-recursive filters. So therefore, their impulse response extends over an infinite period of the time. So because of feedback, so an IARE filter can be implemented with fewer coefficients than for an FIR finite impulse response filter. So lattice filter are simply another way to implement either FIR or IARE filter and are often used in speech processing applications. That's why all our projects, real-time projects based on the speech processing, because of flat text filters, are simply another way to implement either finite impulse response or infinite impulse response, either non-recursive or maybe recursive filter, and are often used in a speech processing application, like either what you call audio processing or entertainment or other cine field. They are implementing by using our digital filter. So finally, so we will export digital filter lend themselves to adaptive filters applications simply because of the what you call speed, because of the speed and what you call easy with which the filter characteristics can be changed by varying the filter coefficients. The coefficients may be what you call either what you call AK or BK value. Based on that, this how they are calculating the AK and BK with reference to that what you call this out of the filter, or maybe what you call impulse response or H of n, or and so on. Okay, like this is the main concept relevant to this finite impulse response and infinite impulse response filter, or recursive distal filter, or non-recursive distal filter. Okay, this all you have seen that. Yeah. Now coming to the design of finite impulse response filter. Design of finite impulse response filter and FIR filter of length m is an linear time invariant system with the following the difference equation, like here. So that means there is a flexibility with this. So there is a features finite impulse response filter design using the window method. Use the Kaiser window or Chebyshev window to specify the filter length, attenuation, and the transition width more precisely. You only have to provide the two parameters, like the third parameter is calculated automatically. What is that all parameter? This is the based on these all features, we try to verify the design this FIR finite impulse response filters. Like this, we will write after completion of this all, or we try to design this type. We will expect this all output response. If it is filter template, or by the multiband, or it is a with reference to that from list, we can try to verify that all the coefficients based on the specification, it is varies, and so on. Sometimes we require the smoothing filter. Use this filter to smooth signals so peaks are to be precise as accurately as possible. Yeah, the CFS filter stands for channel frequency class. A four-pole faceless Butterworth filter used primarily for cross test and implemented what you call in accordance with the ISO 6487. Like this, practically based on these all poles and zeros, we will try to verify in practical aspect after completion of this by using different filters. Here it is, we have chosen only Chebyshev filter. Yeah, there is a possibility with bezels, Butterworth, and inverse Chebyshev and elliptic like this. Now it is I have chosen that Chebyshev with the band pass. So using this all, we can choose the low pass filter with what I call filter signal, or my filter coefficients, or filter signal with a phase correction. Like this, we try to verify and practically using this all analog filter based. So using this all of filter characteristics, you try to verify in the practically. After designing your all filters, we will verify that in practically. So before that, there is a somewhat we require the summary and a comparison of the IARE FIR digital filter. Of that, based on this, we try to what you call design in depth of that. So all design in terms of that what you call mathematical analysis, some calculation. Before entering this all, verifying this all computations or problems and designs, we have to summarize a comparison of the IAR and FIR filter, digital filter, which one is important, which one is suitable for real time or digital era, and so on. For that case, FIR can provide exactly linear phase, and IAR can provide similar magnitude response with fewer coefficients or lower side lobes for the same number of coefficients. Coming to the FIR, finite impulse response designs by windowed sync or frequency sampling are simple. Just now we have seen that number of windowed that either may be what you call Kaiser window, Dollar-Seveshew, what you call, and different windowing techniques. Okay, so using this all windowed sync or frequency sampling are simple. Okay, either Seveshew 1 or Seveshew 2 or what do you call, different windowing techniques, Kaiser window, and so on. FIR equiripple design allow better control of the frequency breakpoint and pass band and stop band. Ripple, it is a more complicated to implement. So, but that was solved 30 years ago. But we are ready to implement in real time. So it is enhanced. So 30 years back they are solved. So using this equiripple design allow the better control of the frequency breakpoint and pass band and stop band. So present scenario, present trends, how it is improved that ripple, it is more complicated to implement or not. But that was solved previously. But nowadays how they are solving, how it is useful. Okay, in IAR, infinite impulse response can be designed by mapping analog filters to digital. Okay, so the binary transformation is the best method for verifying that mapping analog filter to digital. The binary transformation is particularly what you call flexible. Okay, so but frequency wrapping must be taken into the account. Okay, more coefficients closer to the desired response. So wider transition band and less ripple in the pass band while we are using this all what you call IAR, infinite impulse response. If you are using the FIR, finite impulse response, windowed sync or frequency sampling are simple. Okay, but this case using the IAR designed by mapping the analog filter to digital, we have to use the binary transformation or maybe what do you call different but frequency wrapping must be taken into account, more coefficients closer to the desired response, wide transition band, less ripple is pass band. Like that we right go on verifying that each and every vertical parameter are variations. More stop band attenuation. So summary of the trades of like FIR, finite impulse response. Here the linear phase if the symmetry h of n is equal to h of capital N minus 1 minus n if n is equal to 0, 1, 2, 3 and n minus 1. That's easy to design, especially windowed FIR. So IAR never exactly linear phase. Comparably or even better magnitude response as a finite impulse response, but with lower order using the poles and zeros. So like this, that windowed FIR large m versus small m, like magnitude of h of omega, better approximation to desired frequency, sharper transition band, some side lobes have reduced amplitude, peak side lobes in stop band relatively unaffected, more computation or more hardware longer delay. Okay, so like this we like to verify in FIR finite impulse response filter design. It is based on the frequency sampling design method. There is a possibility of it as varies. Easily can compare that which method is suitable for digital era or real time. And Fourier transform design method verify that the FIR is either it is what you call non-recursive or not. Coming to the IARE filter design, so we have to use that this is the popular method, binary transformation method. So of that pole zero placement method. So while they are using this all two FIR or IARE digital filter, major applications are involved here. One is 6 edges human eliminator, okay, or ECG pulse, okay. So yeah, coming to the FIR finite impulse response filter, digital filter design, it is based on there is a definition with this. A finite impulse response FIR, finite is specified by, so what you call in mathematical y of n is equal to the summation I is equal to 0 to k, the coefficients bi into x of n minus I. So the transfer function of the finite impulse response filter, so it is h of z, that h of z is equal to what you call b naught plus b1 z power minus 1 plus b2 z power minus 2 and so on, plus bk z power minus k, where bi is the filter coefficients, okay. So k plus 1 is the filter length and so on. So the difference equation, the difference equation is followed by y of n is equal to b naught of b naught into x of n plus b1 into x of n minus 1 plus b2 into x of n minus 2 plus b3 x of n minus 3 and so on, plus bk into x of n minus k. So like this, using this transfer function of the FIR filter, the difference equation, so right to the realization of the FIR filter, so right to verify this according to this what you call the difference equation, the transfer function of the finite impulse response filter, okay. X of n, here it is, it easily can realize this what you call FIR filter. Yeah, now coming to the Fourier transform design method, this method is we will expect that our frequency response for ideal low pass filter. So already we know that all omega versus z h and t power j omega. Like this, according to our low pass filter, h and t power j omega, it is 1, 0 less than or equal to omega mod omega less than or omega c, 0 omega c less than or equal to mod omega less than pi. This is the inverse Fourier transform. After that, we will expect this impulse response of the ideal low pass filter. So we know that low pass filter, it allows only low frequency component, it opposes high frequency components. Based on that impulse response of the ideal low pass filter, the desired impulse response h of n of ideal low pass filter is infinite and symmetrical about n is equal to 0. Okay, after truncating 2m plus 1 major components using the coefficients symmetric. So it is like symmetric, here it is where h of z, that h of z is equal to what you call h of m z power m plus h of what you call and so on, h of 1 z power 1 plus h of 0 plus h of 1 z power minus 1 and so on, plus h of m z power minus m. Okay, this is all symmetric. Okay, so to obtain the causal finite impulse response h of n is delayed by m samples. So based on this m samples, where h of z is equal to what you call b naught plus b1 into z power minus 1 plus b2 z power minus 2 plus and so on, plus b2 m into z power minus 2 into m. So like this, where it is b naught bn is equal to h of n minus m, for n is substituted, small n is equal to 0, 1, 2, 3 and so on up to 2m. Okay, so you can recognize the will expect its output response like this. So ideal impulse for standard finite impulse response. Here this all are depending upon filters. Typically ideal impulse response, it is followed by h of n non-causal finite impulse coefficients. We have to consider the low pass. H of n is equal to that impulse response while you are using the low pass filter, omega c by pi for n is equal to 0, sine of omega c n by n pi for n not equal to 0. If this case minus m less than or equal to n less than or equal to m. So on using that at the tapper, that m value, that n value ready to substitute, n is equal to 0, 1, 2. This all are depending upon that m, the tapper, not on the filter. Yeah, next coming to this high pass filter where h of n is equal to pi minus omega c by pi. For n is equal to 0, sine of omega c into n by n pi for n not equal to 0. In terms of that, it include minus m less than or equal to n less than or equal to m, and so on. Band pass filter h of n is like this, and where h of n is like this, we can follow. If n is equal to 0, if n not equal to 0, like this. So minus m less than or equal to n less than or equal to m. Band like this, similar to that, the same that band stop, h of n is impulse response, h of n is like this. So best example, finite low pass, finite filter design, finite impulse response design. There is the best example it is given. Design a 3-tap. Design a 3-tap. That means M is given. 3-tap finite impulse response, low pass filter with cutoff frequency of 800 Hz and the sampling rate of 8000 Hz using the Fourier transform. You have to determine the transfer function and the difference equation of the designed finite impulse response system. Next, compute and plot the magnitude frequency response for omega is equal to 0, omega equal to pi by 4, where omega equal to pi by 2, omega is equal to 3 pi by 4 and pi radians. This is the given example. How we are solving, how we are designing with the help of this, and the solution here, normalized cutoff frequency is followed by omega c is equal to 2 pi fc into ts. Here it is that fs is given and ts is also given. According to this, there is a direct substitution 2 pi into 800 by 8000 is equal to 0.2 pi radians. Okay, so coming to the 3-tap filter, that is 2m plus 1. Okay, it is also equal to 3, where m is given, m equal to 1. The tapper is calculated, m is equal to 1. H of n for n from minus m to plus m. So where n is substituted minus 1, 0 and 1. Now that we are to verify that the coefficients, filter coefficients. Okay, h of 0, omega c by pi for n equal to 0. H of n like this, where n not equal to 0. So finally that because impulse coefficient, compute the coefficients, h of 0 equal to 0.2 pi by pi, that is h of 0 equal to what we call 0.2. Similarly, where n is substituted 1, small n is equal to 1. Okay, sine of 0.25 into 1 by 1 by 1 into pi, here typically 0.1871. The coefficients are calculated and measured. So right to match the next, using the symmetric property, that is h of minus 1 is equal to h of 1, 0.1871. Like this, with h of n by 1, b of n, and for n is equal to 0, 1, 2, and so on to n. b0 is calculated, b0 and b1 and b2 like this. So b0 equal to 0.1871 and 0.2, 0.1871. Like this, we need to solve this design aspect. Easily can design by using this mathematical notation. Like this, and coming to the second, the transfer function, like in the causal finite impulse response. So it is, we know that all h of z is equal to b naught plus b1 into z power minus 1 plus b2 into z power minus 2 and so on. Okay, so where bn we know that one, based on that bn value, right, to calculate h of z, that h of z is substituted according to b1, b naught we know, b1 we know, so we know, and it is calculated, b naught we know, b1 and b2 and so on. All of that substitution where h of z is equal to y of z by x of z. Here, using this, directly we write to verify this all. Solve that inverse Z transform. After calculating this solve where y of z equal to this value. So finally, what you call inverse Z transform is involved. The magnitude, frequency response and phase response, where z is equal to e power j omega. After that, in terms of the h of z, so h into e power j omega is equal to e power minus j omega, that 0.1871 e power j omega plus 0.2 plus 0.187 into e power minus j omega. So inverse Z transform, by using this solver h of z, easily can calculate the what you call inverse Z transform. Okay, so now, so we can, it is reflected with the Euler's formula, e power jx plus e power minus jx is equal to 2 cos x. We know that. So of that, using this all, same way h and e power j omega is measured, is calculated, easily can determine that value. The magnitude and frequency, phase magnitude and phase frequency, so it is all are, we will expect due to this all, the magnitude of frequency response and the frequency phase response, where if it is z equal to e power j omega. Okay, the magnitude of h into e power j omega is equal to mod 0.2 plus 0.37, already it is calculated, 0.3742. Okay, like this. So that an angle, this you can at h into e power j omega like this. So you can compare this all, 0 radians omega is equal to 0, pi by 4, pi by 2 and so on. So how it is the varies in terms of the magnitude and degree and angle and so on. Okay, after that easily can measure that this thing. Okay, linear phase will be appeared after similar writing. By using this all mathematical notation, should write a piece of code. We will expect that graphical representation using this MATLAB. The phase, linear phase will be appeared like this. So if filter has linear phase property, the FIR, finite impulse response coefficients, are symmetric about the middle coefficient, and the finite impulse response filter order is an odd number. The output will simply be delayed version of the input. Okay, let 17 tab, that m is given 17 tab FIR filter with what you call linear phase response, m is equal to 8. Consider here, it is observed that m is equal to 8, where m is equal to 8. So it is ripples and what you call, if it is what is the linear phase, or maybe may not be a linear phase. Okay, so where m is equal to 8 sample delay. 8 sample, how many samples delay? 1, 2, 3, 4, 5, 6, 7, 8 sample delay. Okay, so similarly, that if is m here, this case also, you can observe that linear phase. Okay, next coming to this nonlinear phase. The nonlinear phase, input is x of n is equal to, x of n is equal to x1 of n plus x2 of n minus sine of 0.2 and 1 by third, it's like this and so on. Linear phase filter output y1 of n is right to calculate. If it is 90 degrees nonlinear phase filter, y2 of it is followed by y2 of n. So you can consider this is the combinations 2 sinusoidal input. You can consider this is the input. We will expect the linear phase filter output response if m is equal to 8. Okay, so under 90 degrees phase delay, filter output is, it is distorted or maybe accuracy information and so on. Yeah, coming to this finite impulse response filter with the windowing method. So why we are using the windowing method? Because of using the previous methods, always we are calculating what you call linear, non-linear phases. The window function, which is symmetrical and can gradually weight the designed finite impulse response coefficients down to 0 at both ends for the range minus capital M, the taper less than or equal to small n less than or equal to capital M. Apply the window sequence omega n to the filter coefficients. It gives what you call window functions are used to remedy the undesirable Gibbs oscillations. Okay, that's why they are using that all windowing technique. Windowed, it is followed by H W of n is equal to H of n into W of n. Okay, here we should follow this all windowing: rectangular window, triangular window, Hamming window, Hanning, and Blockman windows. Using this all windowing functionalities, so easily can design that FIR filter with a linear phase. The window function, which is symmetrical and can gradually weight the desired finite impulse response with non-recursive filter coefficients down to 0 at both ends for the range minus m less than or equal to n less than or equal to capital M. Okay, so here we'll verify the one example. The example is followed by, in terms of the design, a 5 tap finite impulse response band rejection or band stop filter with a lower cutoff frequency of 2000 Hz, upper cutoff frequency 2400 Hz, and the sampling rate is given 8000 Hz. Using the Hamming window method, determine the transfer function. Okay, so using this best example, the tapper should verify that either symmetric and non-symmetric. That window, Hamming window they are using, how they are determining the transfer function. So on the solution, normalized cutoff frequencies, it is given where omega L is equal to 2 pi FL into T, where FL is given 2000, T is also given 8000. Now so that omega L is ready to calculate. This is normalized cutoff frequencies. Okay, so lower cutoff frequency and high cutoff frequencies. Okay, if it is lower cutoff frequency FLT and high cutoff frequency is 2 pi FHL. Okay, and what do you call 5 tap FIR? That means 2m plus 1 is equal to 5, then m is equal to 2. Okay, like this. So we have to calculate the impulse response where m is equal to 2 is substituted. That's why what do you call m minus m less than or equal to n. Here it is mentioned minus n less than or equal to small n less than or equal to 2. Why it is 2? That m value is decided. The tapper m value is 2, m is equal to 2. That's why it is mentioned. Yeah, normally it is minus capital M less than or equal to small n plus what do you call less than or equal to, okay, if it is less than or equal to m less than or equal to n less than or equal to plus what do you call m. But here m is given, m is calculated. Where it is calculated here, m is equal to 2. Listen that m is equal to 2. Here it is minus 2. Minus 2 less than or equal to small n less than or equal to plus 2. Like this. It is mentioned. It is calculated the impulse response. H of n is equal to like this. N equal to 0. N not equal to 0. We can use that minus 2 less than or equal to n less than or equal to 2. After that, so H of that n value is substituted. If it is a small n is equal to 0, we have to calculate if n is equal to 0 according to this desirable formula, where small n is equal to the first impulse response equal to 0.9. and h of 1, n is small n equal to 1, okay, 1 0, it is calculated, n equal to small equal to 1, 0.01558. So now it is gone now, n value equal to 2. So 0.09355, like this. The symmetry h of minus 1 is equal to h of 1 is equal to 0.01558. Like this, we have to design that desirable filter using what you call windowing technique. Here they are in the window, what you call which window? That Hamming window. Like this. So S2 of n and so on. You will verify that. Okay. So but here according to this we are trying to calculate. Now coming to this, given that Hamming window, due to this Hamming window function, h of ham, h of here it is w is the window, using that Hamming, h of 0 where n equal to 0. Now it is right according to this desirable given formula for while you are using the Hamming window function. So WH Hamming 0 equal to 1, 1.0, 1 equal to 0.54, 2 is 0.05. Okay. So how it is satisfied the symmetric. W of H of Hamming minus 1 is equal to H of W of Hamming 1 is equal to 0.54. Okay. Like this, second, where n equal to 2, now it is symmetric is okay here, and windowed impulse response. This is the windowed impulse response. HW of 0, okay, that is n is substituted here, n equal to 0, n is equal to 0, n equal to 1, n is equal to 2, and so on, symmetric value. So finally it is calculated the Hamming window functions, and windowed impulse response should calculate like this, of that by delaying HW of n by m is equal to 2 samples. M is equal to 2 samples. B0 is equal to B4, B1 is equal to B3. You have to measure these all values. So of that, the transfer function will be observed, where h of z is equal to 0. This value, okay, and this value B3, B1 and B2 value, and where B2 is equal to 0.9 z power minus 2, and so on. This is the finalized transfer function as per by using the windowing technique. This is there is only Hamming window. Suppose you have to verify Anning and Kaiser window and other what do you call Mitsubishi windows and maybe Blackman window and so on. So how it is very well, how it is useful in particular real-time aspect by designing this windowing methodology, use it with help of finite impulse response non-recursive filter. Okay.
Like, share and subscribe. Hit the bell icon for more updates.